In this video, I wanted to walk you through some examples of setting up integrals that can be used to calculate volumes. We recall from back in lesson 12 that the double integral of a function was a measure of the net volume between that function's graph and the xy plane. So we will be doing some practice problems calculating that net volume using double integrals. And we will also be seeing how we can use double integrals to calculate volumes between two surfaces. And I'll give you a heads up right now that in my experience, the hard part of these problems is usually making sense of what is the correct region of integration for the problem. What is the correct R for the problem? So we'll be focusing on that in particular as we go through this lesson. So first example, someone says, okay, I'm thinking of this paraboloid z equals 8 minus x squared minus y squared. So what we can see is this is a paraboloid starting at 8 and then going down from there because we're subtracting x squared and we're subtracting y squared. If I looked at the volume underneath that parabola, then what would that volume be? So let me go ahead and sketch a drawing of this situation. Just a very rough drawing in 3D space. And maybe the drawing will help me to understand a little bit about what the region R should be in the XY plane. So rough sketch of a parabola starting at z equals 8 and coming down from there in all directions. Now, the region R for this problem is going to be the set of all inputs x and y for this 3D object. In other words, the region of integration R is going to be, in some sense, the shadow of this 3D region on the xy plane, which I've shaded here in blue. So if I look at that same picture in the xy plane, just look at the xy plane portion of the picture, my region of integration is going to be the one that looks like this disk of some unknown radius, right? So if I want to find an equation that captures the borders of the region R, I think I will need to figure out exactly what is the radius of the disk that we're seeing here in the XY plane, the disk that we're seeing over here in the 3D drawing in the XY plane. So to understand what the radius of my region of integration would be, I'm going to start by thinking about where this paraboloid is intersecting the xy plane. That's going to give me information about this circular rim of the disk down here in the xy plane. Now the xy plane has an equation, z equals 0. And the paraboloid we're given has an equation of z equals 8 minus x squared minus y squared. So to figure out where two equations intersect, all you have to do is set those two z's equal to each other. And I get z equals 0 equaling z equals 8 minus x squared minus y squared, which I can then rearrange to get x squared plus y squared equals 8, which I can recognize is the equation of a circle, specifically this circle that is formed when the paraboloid intersects the xy plane. And from this equation, I can deduce the radius of this circle. The circle's radius is the square root of 8, or put another way, 2 square root 2. Okay, So now I have understood the region of integration for my problem. My region of integration is a full disk of radius square root 8 in the xy plane. Finally, I just need to take that region of integration and translate it into limits of an iterated integral that I could use to capture the volume under this paraboloid. So I'm going to have to follow the same process, the step-by-step process that we outlined a couple of lessons ago. I'm going to have to draw the region, which I've already done here, and then I'm going to have to decide on an order of integration, dy dx or dx dy. Now, this region of integration is so symmetrical, I don't think it'll make much of a difference. But I personally prefer the order dy dx when all other things are equal, because I'm simply more accustomed to dealing with functions in the form y equals function of x. So I'm going to go ahead with y first so that I can set up these limits in the form y is some function of x. And then I'm going to go into my region and I'm going to hit it with a vertical slash so I can see which curve is forming the bottom of the region and which curve is forming the top of the region. Now what I can see is that the bottom of the region is being created by this bottom half of this circle. And the top of the region is being formed by the top half of the circle. So now I just need to find the formulas for this bottom half of this circle and the top half of this circle. And for both of those purposes, I can use this equation for the circle that we found earlier, that x squared plus y squared is equal to 8. I can solve this for y, starting by subtracting x squared from both sides, and then I can apply a square root to this equation. If I apply a positive square root, the positive square root will give me the upper half of the circle, and that's my top function. If I apply a negative square root, the negative square root gets me the bottom half of the circle, and so that would form my lower function for this region. So this lower function, the negative square root of 8 minus x squared, and here's my top function, the positive square root of 8 minus x squared, in the order y first and then x second. Finally, my outer limits of integration have to be numbers. And specifically, they're going to be the numbers that correspond to the smallest and the largest x-coordinate of the region, which is going to be informed by the circle's radius. If the radius of this circle that we've drawn is square root 8, then that's going to be our positive largest x value. And the negative version of that is going to be our smallest x value on the other side. So those constants are going to be my lower x limits of integration and my upper x limit of integration. So notice something. My region of integration was not in the shape of a rectangle. So as I set up my limits of integration in the dy dx order, I was getting some limits that were not constant, right? If all of my limits were constant, that would definitely be incorrect, because 4 constant limits corresponds to having a rectangular region, and that's not what I have here. Finally, the only thing left to fill in is the integrand, which is the function that I am integrating in the center of this problem. And since I'm trying to find the volume under this paraboloid specifically, the function that I would integrate is the paraboloid itself, which had the formula x minus 8 minus x squared minus y squared. So I would integrate this function as y goes from this non-constant limit to this non-constant limit, and then I would integrate as x goes from this constant limit to this constant limit. And this would tell me the exact value of the volume under that paraboloid, the volume trapped between the paraboloid and the xy plane. Okay, and since they only asked me to set up the integral, that's all that I need to do. The setup is complete, so I can move on. Let's go ahead and do another example. So in this case, I have a tetrahedron, which is basically the three-dimensional version of a triangle, which is formed by connecting a certain number of vertices. So here my vertices are at the origin. Another one is 4 units along the x-axis. Another one is 3 units along the y-axis. And another vertex is 2 units along the z-axis. So let's go ahead and set up the integral that could be used to find the volume of this tetrahedron here. Now, at first, this question might seem a little bit strange compared to the one before, because they're not asking us to find the volume underneath a certain surface. At least it doesn't seem at the beginning like they're asking us for something like that. However, let's go ahead and draw the region in question. We have a vertex here at 0, 0, 0. We have another 1, 2, 3, 4 units out here along the x-axis. We have another one here, which is 3 units along the y-axis, and another one here, which is 2 units along the z-axis. And the tetrahedron is this little wedge shape that is formed by connecting all of those dots. Now, notice something. The volume of this tetrahedron, this wedge shape, is the same thing as the volume that is under the plane that is connecting these 3 outer dots here, right? This slanted plane that is connecting these points 4, 0, 0, 0, 3, 0, and 0, 0, 2, the volume of the wedge is the same as the volume underneath that plane, the volume that's trapped between that plane and the xy plane. So the volume that I want to find is the double integral over the region R of the plane equation, where R here is the shadow of the tetrahedron in the xy plane. In other words, all the x's and y's for all the points in the tetrahedron. In other words, R is this little triangular piece down here in the xy plane corresponding to the shadow or the footprint of the tetrahedron. And if I draw it in 2 dimensions for clarity, then I would be connecting this point 4 units along the x-axis, and this point 3 units along the y-axis, and this point at the origin to form this triangular shadow of the tetrahedron on the xy plane. So in this problem, I have 2 tasks in order to complete this double integral that I need to calculate this volume, right? Task number 1 is to find the equation of the plane in this problem. And then task number 2 is to find out how to translate the region of integration R into limits of integration. So let's take all those pieces one step at a time. Now, back in Calculus 3, you learned a very lengthy process for finding the equation of a general plane between 3 points. And you can certainly use that process here if you wanted to. Subtract the 2 points, excuse me, subtract the 3 points to find two vectors in the plane, cross those vectors to find a normal vector to the plane, and then use the normal form of the plane to get the equation. I am not going to do that. I am going to use a special equation that you can use for a plane when you know the three intercepts for the plane. The place where the plane intercepts the x-axis, the place where the plane intercepts the y-axis, and the place where the plane intercepts the x-axis. I'm going to use the fact that we have these three very special pieces of information about the plane in this case. If you know a plane's intercepts, A00, 0B0, and 00C, the equation of the plane can be written in the following format: x divided by the x-intercept, y divided by the y-intercept, z divided by the z-intercept, all equals 1. Is a special formula to find the equation of a plane when you know its three intercepts. So in our problem, we were told that the x-intercept was specifically 4, the y-intercept was specifically 3, and the z-intercept was specifically 2. Now I need to rewrite this plane as a function of x and y so that I can complete the double integral in the order dx dy or dy dx. So I'm going to take this equation and isolate the output z. I'm going to start by subtracting all the terms that don't contain z, and then I'm going to multiply by 2 to get z fully isolated. And so here is the equation of the plane in the problem. The equation of the plane in the problem is the function 2 minus 1/2 x minus 2/3 y. This is the function of x and y that represents the plane, and I'm trying to find the volume underneath that plane. So that equation that I've just found is going to form my integrand here. The f of xy that I'm integrating is 2 minus 1/2 y minus 2/3 y. 1/2 x, 2/3 y. Okay, now that I've figured out what I am integrating, the next step is to translate this region R into limits of integration for a double integral. So to that end, I'm going to have to decide first on an order of integration for this region. Now, as before, unless I have a good reason to integrate with respect to x first, it is generally my preference to integrate with respect to y first, because I am simply more comfortable with y as a function of x, because that's what I have done in algebra, in pre-calculus, in calculus. So if I choose that particular order of integration, I'm going into this region and I'm thinking about what functions bound this region on the top and on the bottom. Now I can see that the bottom function for this region, the curve that is crossed first by this line as it first enters the region, is this horizontal line sitting on the x-axis. And as usual, the equation for that portion of the x-axis is the constant function y equals 0. And then the function forming the top border of the region is this slanted line. This line here that connects this location 4 units along the x-axis and this other location, which is 3 units along the y-axis. So from these 2 points, I can find the equation of the line pretty readily. It looks like the slope of the line, if I do rise over run, is going to be 3/4, because that's 3 minus 0 divided by 0 minus 4. And I can see the x-intercept, excuse me, I can see the y-intercept, b equals 3 is our y-intercept. So as we set up our double integral to calculate the volume of this tetrahedron, we now have filled in a lot of the blanks. We have filled in the integrand. The function that we have to integrate is this plane, 2 minus 1/2 x minus 2/3 y. If I decide to integrate with respect to y first, our lower y limit is the constant function y equals 0, and our upper y limit is this linear function, negative 3 over 4x plus 3. We are almost there. The only thing that's left to do is to identify what our outer x limits should equal. And to that end, we just have to think, what is the smallest x coordinate for my region R? And what is the largest x coordinate for my region R? It looks like the smallest x coordinate is x equals 0 here at the left corner. And here the largest x coordinate is x equals 4 at the bottom right corner. So those constants would correspond to those x limits of integration. Once again, I can't emphasize enough that because our region of integration was not a rectangle, one of our limits of integration was non-constant. Here we had a triangular region, and so we ended up with the non-constant limit of integration here, in particular at the top of my y limits. Finally, let's talk about how double integrals can be used to find the volume between two surfaces. Up to this point, we've been dealing only with the volume between a surface and the xy plane. But what if we had two surfaces and we wanted to find the area between them? The formula that we will use in Calculus 4 for this purpose is very similar to the formula that you use in Calculus 2 to find the area between two curves. When you are trying to find the area between two curves, a top function g of x and a bottom function f of x, you're trying to find the area between them. Then you took an integral of their difference. The highest function, the function on the top of the region, g of x, minus the lowest function, the function on the bottom of the region, f of x. Then you integrated that for the smallest x value to the largest x value. Integral from a to b, g of x minus f of x dx. And this, of course, assumes that g of x is the bigger function, the taller, the higher function between the two. If f of x was the one that was on top, so to speak, then it would be f of x minus g of x. Now, in Calculus 2, the formula is very, very similar to find the volume between two surfaces. If I have a surface on the top, for example, maybe the surface g of xy is a paraboloid opening down, and maybe the surface f of xy is a paraboloid opening up, and you want to know how much volume is trapped between those two surfaces. You can measure that using a double integral instead of a single integral. A double integral of the surface on the top minus the surface on the bottom. Integrate that over the region R, where R corresponds to all the x's and y's for this volume. So let's give an example of setting up a double integral that could be used to calculate the volume between two surfaces. Let's try to set up a double integral that could be used to calculate the volume between the surface z equals 3 minus the square root of x squared plus y squared and the surface z equals 1. As usual, I'm going to start with a very rough drawing, first in three-dimensional space of the three-dimensional volume that I'm trying to find. And then I'm going to translate that into a two-dimensional drawing of just the xy plane and the region R of integration. Now, surface number 1 here, I recognize as the equation of a cone. A cone that starts at z equals 3 and then opens down because we're subtracting the square root of x squared plus y squared. So I have a cone that starts at 3 and then opens down from there. And normally that cone would extend down forever, but I'm only interested in the volume of the region between the cone and this flat plane sitting here at z equals 1. So as soon as we hit the plane at that level, z equals 1, we're going to stop the cone there. And the volume that we're trying to find is the volume that is under this cone but above this plane. So I'm going to look at the shadow of this region on the xy plane. The shadow, I'm going to look at all the x and y coordinates for points in that volume I'm trying to find. And I can see that the shadow of that cone on the xy plane once again has the shape of a disk. So if I can determine the radius of this disk, then I can create the functions that describe the top and bottom borders of this region. To determine the radius of the shadow, I'm going to look for the place where the cone and the plane intersect, because where the cone and the plane intersect in this picture will correspond to this outer rim of the volume, and that in turn will correspond to the outer rim of the shadow. So I want to take the equation of the cone and set it equal to the equation of the plane to see where they intersect. So let me go ahead and rewrite this equation so that it's in a slightly simpler format. I'm going to start by moving the square root term to the other side to make it positive and subtracting 1, giving me the square root of x squared plus y squared equals 2. which alternatively you could think of as x squared plus y squared equals 4. So this outer rim of the region I recognize as a circle of radius 2 from the square root of 4. So that means my region of integration has as its bottom function the function that corresponds to the lower semicircle of radius 2, y equals the negative square root of 4 minus x squared. And the region of integration has as its top function the positive square root of that equation, y equals positive square root of 4 minus x squared. Additionally, that information tells me that the x coordinates are extending from negative 2 on the far left to positive 2 on the far right. So this allows me to finish setting up our limits of integration. The x values go from negative 2 to 2. The y values go from the negative square root to the positive square root. And this is for the order dy dx, which I've said many times is my favorite. So here are the limits of integration. And the last thing that I need to think about is what would be the integrand? What would be the function that I have to integrate to find the volume described here? And for this, I'm going to remind myself that to find the volume between two surfaces, my integrand should be the difference between those surfaces as functions of x and y, starting with the top function and then subtracting the bottom function. Now, in this problem, I can see from my three-dimensional picture that the cone is the surface on the top of this region, and the plane is the surface on the bottom of this 3D region. So based on that, I would set up my difference in the order with the cone first, and then subtracting from that the equation of the plane, both as functions of x and y. Now, if I were working on a different problem where maybe the plane was the highest surface and I had some cone which was underneath the plane, then the subtraction would be in the other order. And this is just necessary to make sure that my volume works out to be positive. This is a regular volume calculation. They're asking me for volume. They are not asking me here for net volume. So if we were actually asked to calculate this integral, which they're not asking us to do, but if they did, I would be expecting an answer which is positive rather than negative, because regular volumes always have to be positive. Okay, so a final example here of volume between two surfaces. Here I'm asked for a double integral that could be used to calculate the volume between this paraboloid that starts at 4 and opens down, and this paraboloid that starts at the origin and opens up. So let me begin with my rough drawing, my rough sketch in 3D space, and then I will look at the shadow in 2D space. So roughly speaking, here is my paraboloid opening up from the origin. Roughly speaking, here is my paraboloid opening down from 4. And so the region between those surfaces as a kind of weird egg shape, like an egg with a weird, like, ridge on the outside of the egg. Now, let me look at the shadow of this three-dimensional region as cast down onto the xy plane. The shadow of this egg shape cast directly down onto the xy plane, it looks like we'll form a circle slash a disk once again. And it looks like the outer rim of that disk will once again correspond to this ridge right here where the plane, where the paraboloids intersect one another. So to understand that location where the paraboloids intersect to create this ridge which forms the outer rim of my region R, I'm going to take the equation of the paraboloid that opens down, and I'm going to set it equal to the equation of the paraboloid that opens up. If I solve this to rewrite it in a more familiar format, first by gathering all the like terms together and then dividing out that 2, I find that this outer rim here of my disk, of my region of integration, is a circle of radius square root 2. So based on that, we would have limits of integration that are quite similar to what we had in the previous exercise. The y would correspond to the negative square root as the lower limit, the positive square root as the upper limit, in the order dy dx. The lower x coordinate would be negative square root 2. The upper x coordinate would be positive square root 2. And that just comes again from the functions that bound this circle on the bottom and on the top, and the coordinates that form the left edge and the right edge of the disk. The only thing left to determine to finish setting up this problem is the integrand, the function in the center that we are integrating. And we remember that this can be found by subtracting the top surface and the bottom surface, both expressed as functions of x and y. In my picture, I can see that the top surface is formed by this paraboloid that starts at 4 and goes down from there. And I can see that this other paraboloid, starting from the origin and opening up, that's the surface on the bottom of this volume. So I'm going to set up my integrand in the form top surface, that entire equation, minus bottom surface, minus that entire equation, minus the entire formula, x squared plus y squared, as a function of x and y. And so this would be the double integral that could be used, in theory, to find the volume between those two surfaces.